Hello class. We're now going to take a look at reactions with alcohols. So let's take a look at a tertiary alcohol first. So what if we had tertiary alcohol that looked like that? Recall when we treat it with HX, we can get the OH right here to leave, and then we could make ourselves a tertiary alkyl halide. So how does this happen? Remember that OH is not a good leaving group. So we have to convert it into a good leaving group first. And the way that we do that is by protonation. We can take the lone pairs there on the alcohol. This hydrogen is electrophilic because of the electronegativities of the halogens. And so that's going to come in and abstract that, like so. And that's going to give us, let's go down here now. Why is that so important? Because now we've made water. And water is a good leaving group. So the next step would be for water to leave. And that's good. That's okay, and that will happen because what have we just generated here? We've generated a tertiary carbocation. But remember that in this step right here, when this alcohol grabs that proton, we also have what's left over, which would be the halide. So this halide now is nucleophilic, and that's going to have 4 lone pairs. So it can use one of the lone pairs to attack that carbocation to generate our product. And so when we have a tertiary alcohol, the mechanism is a SN1 mechanism. But if we change the way that change the degree of alcohol to primary or secondary, then we're going to have a SN2 mechanism. So let's take a look at that. So let's take a look at a primary alcohol. What if we want to get that to a alkyl halide like HBr? Well, you could treat it with HBr. And so in a SN2 style reaction, we still need a good leaving group. And hydroxyls are not good leaving groups, so we need to convert it into a good leaving group by the protonation step. And so we would take that, and that looks like this. So now we have a protonated water there, plus our bromide floating around. Now that's a good leaving group. But this is primary. So does it just leave like this? If it just left, what would we be left with? We would have a primary carbocation. So that is not a good mechanism because we don't generate primary carbocations. And I said that this whole mechanism is a SN2 mechanism. So now that we have the bromide, we have a good leaving group, we would just have to take and do an SN2 style attack right there, and then that would attach our bromine right there. And what else would be left over here? We would have our water. So if you want a bromine on an alkane, you can convert an alcohol into a alkyl halide using it with HBr. Now what if you wanted a chlorine atom? Right. So you could envision something that looks like this. Change that to a chlorine, right? And based off of what I've done, you would say, hey, yeah, that should work. And I would agree, but experimentally, trying to attach a chlorine is just a little bit more difficult than attaching a bromine. And so what you have to do is you have to soup this up a little bit. It's still an SN2 mechanism, but you have to add a catalyst. You're going to add zinc chloride. Okay. So that the mechanism changes slightly here. It's still going to be SN2, but now what's going to happen is something a little bit different. So what happens here is that we're going to have a coordination here. Grab this color. So the lone pairs on the alcohol are going to coordinate with the zinc chloride. And that's going to give us a species that looks like this. I'm going to draw the hydrogen over there. Zinc chloride right there, so that's positively charged, and that would be negatively charged. Okay. Now, what we have going for us is that we still have HCl. Right? And HCl is a strong acid, so it completely dissociates when you're in water. So we're in water there. And so what's going to happen is that's going to be completely dissociated. So we could really visualize the chloride like that. Okay. So we have a lot of chloride floating around also because we have the strong acid right there. And so this chloride is going to have 4 lone pairs. So it's going to use one of its lone pairs to do a SN2 type style reaction like that. So what's that going to do? That's going to make our attach our chlorine to our alkane, and that there's our target. So that process right here, that is definitely SN2. Backside attack kicks it off. So these last 2 reactions that I shared with you can happen with primary alcohols and secondary alcohols. Let's see, let's talk about another, let's see here. Let's talk about another way to attach bromine and chlorine. Yeah, that'll be a good way to do this. So let's talk about that. So let's start with chlorine. Yeah. So what example did I just show you? Let's get a different marker. So I just showed you that if you treated this with HCl, and then you have, and HCl is going to have trace amounts of water in there anyway. But if you want, let's put our water there, and then our zinc chloride, right? That would give us that. But we could also do a different reaction right there, and we could treat that with thionyl chloride, like that, and add some pyridine. And when we add the pyridine, we are going to generate the same product as above. It's just now we're using a different reagent. And so that different reagent, let's take a look at it mechanistically of what's happening here. So I'm going to take thionyl chloride right here and expand it out. Okay. And the first step in this mechanism is the alcohol is going to come in, attack the sulfur like so, and that's going to then break that sulfur oxygen double bond. And so that's let's go over this way here. So what's that going to make for us? We will have, we'll draw the hydrogen that way this time. I'm missing a carbon. Like that. Sulfur, O minus, chlorine, chlorine. So that's going to collapse down. So we have 3 lone pairs there. That's going to collapse down and kick off one of the chlorines. Okay, let's see how much space we have here. But when we take a look at this oxygen, that has only 1 lone pair and 3 bonds. So that has to be positively charged. Is that still on the screen? Barely. I'm just going to draw a shorter bond here so we can see it. Okay, and that's still positively charged like so. And so the next step would be our pyridine. No. Like that. Pyridine's just a base. So that base is going to come in and grab that proton, giving the lone pairs back. So that's going to be O, S, like so. Now what did we generate in this step right here? See how we kicked off a chlorine? So we have a chloride ion now floating around. And so what have we done here is that we've just converted the alcohol right here into a good leaving group. So now our chloride can come in and attack SN2 style and kick off that leaving group. And when you do that, that would then give us our product. Right there. Okay, so do you see how this reaction here gives us the same product as when you use thionyl chloride and pyridine? Pretty slick. Okay. So make sure you understand the mechanism here. Make sure you see that what's happening in this step. This step right here. No, this one. Where this comes in and attacks right here. What type of way? How is that happening? SN2 style. Okay. Backside attack kicks the guy off. Now this reaction right here, okay, this is another key point to remember, because based off of the mechanism, it's doing it's doing an SN2 attack. So that means this reaction can only work with primary and secondary alcohols. If you try to do this reaction with the tertiary alcohol, it would not work because it can't do backside attack. Okay. Recall that if we had an alcohol like this and we treated it with HBr, that would give us this product, right? Well, there's another way to do this exact same transformation. All right, we're going to do the same exact transformation, but we're going to use a different reagent. And that's with phosphorus tribromide, PbBr3. Now this reaction also can only be done with primary and secondary alcohols. Okay. This reaction up here can be done with primary, secondary, and tertiary. But when they are primary and secondary, it's going to follow an SN2 mechanism, and when it's a tertiary, it's going to follow an SN1 mechanism. But because this reaction right here proceeds by a SN2 type mechanism, it can only react with primary and secondary alcohols. So we take a look at the mechanism here of how this works. It's really a quite simple mechanism. And we take our phosphorus tribromide And I'm going to expand it out. Like so. Our alcohol is electron rich, so it's going to attack the phosphorus. Okay. And as it attacks that phosphorus, that's also going to kick off the bromine. And so that's our first step right there. So that's going to give us, draw a hydrogen there, Br2 plus our bromide fell off. And our alcohol has to be positively charged. Now we have bromide just floating around, so we could say, hey, that's just going to come in SN2 style. And so that will go right to our product. And then what else would be left over here? There'd be this byproduct right there that we don't need to worry too much about. That's not what we're interested in. We're interested in making our alkyl halide with our phosphorus tribromide. Okay? So I want you to, that's a very simple mechanism using our primary alcohols. But you have to understand this concept that it's SN2. So what is that going to do when you have a stereocenter? So for example, what if we had a secondary alcohol that looked like this? Secondary alcohol that looks like that. That right there is a stereocenter. It is also a secondary alkyl halide, or secondary alcohol. So if I treated this with phosphorus tribromide right here, what is my product going to be? Is it going to be this? Or is it going to be that? Or that? And if I call that A, B, and C, or would the answer choice be a mixture of B plus C? Well, one thing I hope that you notice is this answer A should be eliminated completely because we have a stereocenter. It started as a stereocenter, and we have to still determine the stereochemistry. Based off of the mechanism that I've just taught you, I told you that this is a SN2 mechanism. So that means it has to do backside attack, which means it's going to invert the stereocenter. So the only answer that makes sense would be answer C. That is the only product that you would find. You would not find a mixture because it's SN2. So you would see that same process if I change these reagents to thionyl-chloride. If I changed it to thionyl-chloride and some pyridine, the answer choices would change here a little bit. We would just put the chlorine. There's our chlorine, right? What would the answer choice be? It would still only be C because it proceeds by an SN2. Right? Okay, another reaction that we can do let's take a look at this. So let's take a look at what if we wanted to let's do a secondary alcohol. So if we have an alcohol here, what if I wanted to convert it into a chlorine, like so? I've already showed you two ways that you could do this. Let's look at a different way now. What we could now do is treat it with tosyl chloride and pyridine. Now, I've already shown you this reaction in previous videos, but what do you see here? It is proceeding by a SN2 mechanism. Very, very important to go back and review that reaction right there. Okay. And so that's taking an alcohol and treating it with tosyl chloride and a little bit of pyridine will give us this that product right there. What if I wanted to have a bromine? Okay. Well, let me show you this stepwise real quick here, okay? So I'm kind of missing a step here. So let's do this the right way. So the purpose of tosyl chloride right here is to convert your alcohol into a good leaving group. Okay. And then after you have your good leaving group, then you can treat it with something else. So let's say a chloride ion, and that's going to proceed via an SN2 mechanism. So we will see here that that's going to do backside attack. And then that will generate a product. Okay. Like so. Okay. That's the better way of talking about it. Tosyl chloride converts our alcohols into good leaving groups. Okay? But look at what happens here. When you put the tosyl group onto the alcohol, do you see how the stereocenter was not affected? It stays, here's a wedge, it stays a wedge. And then when you take a chloride ion that you've added in, it will then attack. And so this right here, this chloride is being added. Okay? We could add, let's say, sodium chloride, just another reagent to get this chloride to come in and react. So we could also do something if we wanted to have a bromine there. What if we treated this with tosyl chloride and some pyridine, all right? And then in step 2, we treat it with, let's say, sodium bromide, like so. What would our product be? So let's draw some answer choices. Like so. What's our product going to be? Well, it's going to proceed by the same mechanism as above here. So our first step is going to convert our alcohol into a good leaving group, like that. And then we can treat that with step 2, which is just going to be the bromide. And so that's going to be backside attack, SN2 style. And so that's going to form only what? Only that product, because it proceeds by an SN2 mechanism. Very, very important to see that. Now I want you to pay attention to these reaction conditions here. So what if I had an alcohol like that? Okay. And I wanted to get it to look like that. What reagents would I use? Or what if I wanted it to look like this? what reagents would I use to get that transformation? Now we have to think about the mechanisms very, very carefully here. So if we want to attempt this top one here, what if I treated in step 1, I treat it with our tosyl chloride and our pyridine. And then in step 2, I add in our sodium bromide. Do you see in this process that I'm going to invert the stereocenter? So go back to the mechanism and you'll see that. But what if I wanted this compound right here? How could we do that? Let's think about this. So we're going to have to invert some stereocenters. And we're going to have to, in this particular one, we're going to have to do it twice. So in order to do this transformation, we're going to have to do a couple steps here. All right, so let's put it over here. So if I took this alcohol right here, treated it with tosyl chloride and our pyridine, step 1, what's that going to do? That's going to convert it into that. And then what if I treated it then with sodium hydroxide? Then we could envision what? An SN2 type thing here, right there. So that would give us that one. And then if we treat that with the phosphorus tribromide with some pyridine, we don't, let's see here. Typically don't need pyridine. And then what would that do? That would do another SN2, invert the stereocenter to give us our bromine like that. All right. So the moral of the story here is that sometimes it looks like a simple transformation, right? Just replace the OH with the Br. But the stereochemistry is critical, so you have to go about it in a roundabout way to do that, okay? So be aware of that. Now let's take a look at tertiary alcohols, and now what we can do is, instead of doing a substitution reaction, we can do an elimination. So for example, if we have ourselves a tertiary alcohol, like so, and we treat it with sulfuric acid and add some heat, then we can generate an elimination product that looks like that. And there's going to be some water left over. You can also do this same transformation with phosphoric acid. If you add phosphoric acid and some heat, this transformation would be the same. But when you use these two acids, there's going to be trace amounts of water in them. And so when we take a look at the mechanism, and I'm going to focus my mechanism with the sulfuric acid, what is going to happen is that we want to do an elimination reaction. And with a tertiary alcohol, we're going to do an E1 mechanism. And in order to do an E1 mechanism, we need to get the group to become a good leaving group. So if we take a look at sulfuric acid, we could also look at it as hydronium, because there's trace amounts of water, and it's going to form hydronium. And so we can convert our alcohol here into a good leaving group by converting it into water. And we've generated some more water right here. And so I already told you it's an E1 mechanism, so that means that the water's going to leave, and that's going to generate our carbocation. Now our water here now can act as a base. Okay? And so this base right here can take one of the hydrogens that's attached there and come and grab it and form our product. So that goes to our product right there. So that is an E1 mechanism where we can eliminate water and go from an alcohol to a alkene. Pretty slick. Now, let's use our orgo knowledge, what we've seen before, and principles that we know. And based off of knowing the mechanism here, if we take this tertiary alcohol right here and treat it with H2SO4, which is going to be the major product? Do you think it's going to be that one or that one? Which one is the major product? Well, if we go through and look at the mechanism here, what's the first step? It's going to abstract one of the acidic protons, right? Whoops, that one. Let's redraw that. So we have our hydronium right here. What's the first step? It's going to grab the proton, right? And then, so that's going to come down here. It's going to be water now. The water's going to leave because we're invoking an E1 mechanism. Now we have a tertiary carbocation plus water. So when we take a look at that tertiary carbocation, do you think it's going to rearrange? No, it's not, because it's already a tertiary carbocation. But we do have a hydrogen coming off here and a hydrogen coming off of here. So this water molecule that's going to act as a base can abstract this guy. And if that did that, like so, that would generate that product. Or if I redraw this molecule, there's our carbocation, there's our hydrogen. What if the water instead took that proton? And then that would lead us to that product. So taking a closer look at that, can you tell me which one's going to be the major product? This one or this one? Well, this one is going to be our major. And this would be our minor. And the rationale behind that is this alkene right here is more substituted, more stable, more favorable. Okay? So this one is what? A tri-substituted alkene, and this is a di-substituted alkene. Okay, so pay attention and be careful of that. If we have a tertiary alcohol, we can also do an elimination invoking an E2 mechanism. And in order to do that, we have to still convert our OH into a good leaving group. And the way that you do that is you treat it with a tosyl chloride right here and our pyridine. And so that's going to generate that species right there. Give us our tosyl group there. And then what you can do is you can treat it with a strong base, ethoxide, and add some heat. And the ethoxide right there is going to be negatively charged. And so what we can do is invoke, hey, there's a hydrogen coming off there. Now, how do you know which hydrogen to abstract? Well, you identify the carbon that is attached to the OTS. And then you just have to go to an adjacent carbon. That is an adjacent carbon, find a hydrogen, and abstract it. So you abstract it, break the carbon-hydrogen bond, bring it down to form the alkene. But now this is a good leaving group, so that leaves. And then that's going to generate our product. So when we take a look at a tertiary alcohol like this and treat it with tosyl chloride and pyridine, step 1 and step 2, and then we add a base with some heat, that will give us our product. Okay? But then if you had the same starting material right here and you treat it with sulfuric acid or phosphoric acid, you're going to generate the same compound or the same product, right? But what's the difference between these two? Yes, you get the same product, but we need to understand it at a deeper level here. Markers aren't, they're dying out here. This one up top right here proceeds by a E2 mechanism, and this one below proceeds by an E1. That's the difference. So with this type of reactions, since it's an E1 and it generates a carbocation, then carbocation rearrangements are possible. But if you invoke this one, there's not going to be any rearrangements. And what's the requirement for E2 reactions? Anti-periplanar. All right. Now we're going to take a look at oxidizing alcohols. Now we have to understand the difference between a primary, secondary, and a tertiary alcohol. So the oxidation reactions that we are looking at has to have at least one hydrogen attached to that carbon that the alcohol is attached to. You have to have at least one. So for a primary alcohol, you have two. So that's great. In a secondary, you have at least one. So that works. But when you look at the tertiary, there's no hydrogen on that carbon. So all the reactions that I'm going to show you now about the oxidation of alcohols does not work with tertiary alcohols. It only works with these two. Okay? That's a very, very important thing to remember. So now let's take a look here. So there's a lot of reactions or a lot of reagents that you just need to know. And I'm not worried about the mechanisms for the oxidations. Does your textbook have some of the mechanisms? Yes. But I'm not going to test you on any of those. They're just a little complex. Some of them I feel are more graduate level type of mechanisms. For example, the Swern oxidation. So Swern oxidation, you can learn it as an undergrad, but I think it's more of a graduate level type of mechanism. But either way, you don't need to know the mechanism. You just need to know the overall transformation. That's the important thing. Let's see if we have some newer markers here. Let's try this one right now, okay? So let's take a look at some reactions here. So let's just take a generic alcohol here. What type of alcohol is that? That is a primary alcohol. Okay. So if we take a primary alcohol, let's get my list here of oxidation here. If you take a primary alcohol and treat it with chromic acid. Chromic acid. Now chromic acid can come in different forms. It can come in, looks like this, Na2, Cr2O7. And you're going to take this salt and treat it with some sulfuric acid and some water. Right? So that's one way that you could see chromic acid. And another way that you can see chromic acid, let's see here. I'm trying to find it here. You could also look at it in this version here. No. O3. I don't want to be misleading here, so let me double check something. So what we have here are two sets of reagents. We have our sodium dichromate right here. And when you take sodium dichromate and treat it with sulfuric acid and water, you generate chromic acid. And chromic acid looks like this. Okay, so that's chromic acid. And that is generated from these conditions right here. You can also treat it with our chromium trioxide, sulfuric acid and water, and then that species right there will also generate chromic acid. So those are the reagents and how you could see them. It's just, I want you to realize and understand that this is not chromic acid. It generates chromic acid. So when you generate the chromic acid, and you have a primary alcohol. Primary alcohols with chromic acid turn into carboxylic acids. So really, you see how there's the alcohol there? And it's still there? All I do is put a double bonded O onto that carbon. And so what have we done? We have oxidized it. We've turned this primary alcohol into a carboxylic acid. What if I take a secondary alcohol and treat it with chromic acid? What am I going to get? I'm not going to get a carboxylic acid because this is secondary. Okay? In a secondary, all I'm going to do is put a double bonded O. So I get rid of the hydrogen and just put a double bond. So I've generated what? A ketone. So with chromic acid, if it's a primary alcohol, it goes to the carboxylic acid. If it's secondary, then it goes to the ketone. All right? So now it's just going to be a difference. What's going to happen with different reagents, okay? So we have a different reagent. Let's see here. Watch what happens now if we change this reagent right here to PCC. PCC. Now PCC stands for this really long name, so I'll write it up here. Pyridinium chlorochromate. And let's draw what that looks like over here, okay? So PCC looks like this. We have a 6-membered ring. Like so. That's going to be protonated. All right, so now it has a charge onto it. And then we have our CrO3 Cl. You can still see that on the screen, good. And that's going to be negatively charged. So you can see that it's a salt, positive and a negative right there. That right there, that's our pyridinium chlorochromate. Okay? There's our species, and we just abbreviate it PCC. When we take a primary alcohol and treat it with PCC, we do not generate the carboxylic acid. What we generate is the aldehyde. So the chromic acid is a stronger oxidizing agent. It takes the primary alcohol and goes all the way to the carboxylic acid. It's more oxidized. However, PCC is not as strong as an oxidizing agent because it stops at the aldehyde. So to be a little bit more accurate here, when you take a primary alcohol and convert it and use chromic acid, it actually happens in stepwise. If you do chromic acid, it first converts it into the aldehyde, like this, and then it oxidizes it further into the carboxylic acid. Right? So chromic acid just does it stepwise. But when you do this reaction with PCC, it stops at the aldehyde and cannot convert the aldehyde into the carboxylic acid. So it stops. So PCC with a primary alcohol goes to the aldehyde. However, if you take PCC and treat it with a secondary alcohol, it goes to the ketone. So with secondary alcohols, chromic acid and PCC give you the same product. But with primary alcohols, PCC and chromic acids do not give you the same product. All right. Let's take a look at another reaction right here. All right. The next one that I want to talk about is called the Chlorine oxidation. The Chlorine oxidation, the reagents for the Chlorine oxidation is a two-step process, okay, where you take DMSO, and COCl, put that in parentheses, put the subscript of 2. And that is called oxalic acid. Where's the, there. Sorry, not acid, oxalochloride. Right there. So the first step is you take DMSO, oxalochloride, treat it with your primary alcohol, and then in step 2, you add triethylamine. When you use those conditions, and you take a primary alcohol and treat it with the Chlorine oxidation conditions, you generate the aldehyde. All right. If you take a secondary alcohol, treat it with the Chlorine oxidation conditions, you will then generate a ketone. All right? So secondary alcohols, Chlorine oxidation, chromic acid, and what was that, PCC? All same product. That's not the case with primary alcohols. We've got to be careful with those. Okay? Now let's see, I think there's one more oxidation reaction that I want you to know. And that's called the Des-Martin reaction. Okay? So let's take a look at the Des-Martin. So I'm going to clean up this board. So the last reaction that I want to talk about is the Des-Martin. Now the Des-Martin reaction, we just abbreviate it DMP. DMP. And the DMP stands for Des-Martin per iode. So this iode right there is responsible for the iodine right there. See it? So the Des-Martin per iodinane, that's a mouthful. So we just say DMP, or just Des-Martin for short. We can take this reagent right here, okay, and treat it with primary alcohols, and what are we going to generate with DMP? We take primary alcohols and convert them into aldehydes. Whereas if we take DMP right here, a secondary alcohol, DMP is going to convert it to the ketone. So really, when you look at all these reactions that we've gone over, secondary alcohols always give us the same product. It is the primary alcohols that differ. So with primary alcohols, if we just go through it real quick, primary alcohols with chromic acid gives you a carboxylic acid. Primary alcohols with DMP gives you an aldehyde. This primary with PCC gives you an aldehyde. And then the chlorine oxidation gives you an aldehyde. Okay. Things to just remember, you don't need to know the mechanisms for these oxidation reactions. Okay? So it looks like I am over time with this video. And so as always, if you guys have any questions or concerns, please reach out. I'll be more than happy to help.